Welcome to Net 101, hybrid networking for millions of users with GCP and Twitter engineering. My name is Cynthia Thomas. I'm a networking specialist at Google Cloud, and I'm accompanied by Todd.
Hi, I'm Todd Segal. I'm a software engineer at Twitter working on traffic and our edge infrastructure.
Today, we're going to talk to you about how Twitter manages traffic to handle millions of tweets and leverages Google networking to augment their capacity. Let's get into it. Twitter is leveraging Google Cloud products that are built on Google's proven infrastructure. You're probably able to recognize some of these logos here. We supported over 1 billion users on 9 products, all relying on Google networking infrastructure. We've learned a lot and innovated a lot to be able to achieve such scale while ensuring reliability, speed, and security. That means better reliability and performance than the public internet and other cloud providers. Through this experience, we've been able to develop protocols that improve networking performance, like BBR and Quick. BBR improves the previous TCP congestion algorithm, which was based on packet loss. Instead, Google has designed an algorithm to respond to actual congestion for available bandwidth and minimal round-trip times for huge performance gains. Another example of Google networking innovation is Quick. It's based on UDP, a transport layer protocol that reduces latency by eliminating the number of handshakes compared to HTTPS over TCP. Twitter and Google Cloud users already benefit from these higher throughput, lower latency gains by accessing Google managed services like Bigtable and cloud storage. By the current numbers, we have 24 cloud regions across the globe, and several more coming down the pipe. As you can see, Google's made a large investment in infrastructure globally, including undersea cables, cloud regions, and partnerships with ISPs to deploy POPs and CDNs at the edge. We continue to grow our data center and cloud region count each year. This benefit means we can rely on Google engineering to deploy reliably and securely across the globe to benefit, for example, a Twitter user anywhere in the world for a better user experience. Here we can see Google's made a sizable investment in physical infrastructure globally. Google has built its own backbone, providing private connectivity between Google Cloud regions, data centers, and such. Just as Twitter has leveraged Google infrastructure for cloud services like Cloud Bigtable, edge networking, cloud storage, Google Cloud users can also benefit from Google's dedicated infrastructure for performance and security. As Todd will discuss, Twitter has complemented its own infrastructure by bursting and adding capacity using Google's global footprint. Twitter is already taking advantage of Google Edge networking, including our POPs for private dedicated interconnects, peering, and our Google front ends for caching, load balancing, and securing against DDoS at the edge. One major differentiator for Google Cloud Networking is the shared global VPC model. So Twitter takes advantage of this model where the shared VPC allows centralized management of Google Cloud Networking. So that means subnets and routes are reachable across the entire global VPC, which means great ease of management while never traversing the public internet. Additionally, this means you can deploy Google global constructs like the Google Global Load Balancers to deploy Anycast VIPs, minimizing the amount of configuration and providing a great end user experience. So there's a host of Google Cloud networking products and capabilities that Google Cloud provides, powered by our proven infrastructure. We have various ways to connect your on-prem to our cloud, secure your workloads with numerous security options, and scale applications through our load balancers and cloud CDN. And furthermore, take advantage of orchestrated workloads through open source standard platforms like Kubernetes and Istio, the roots of which come from Google. So during this talk, we'll discuss some of the edge networking features that Twitter leverages from Google to scale. This includes the Google Global Load Balancer and Cloud CDN. Next, Todd will get into how Twitter deploys at the edge.
Thanks, Cynthia. So I'm going to talk a little bit about Twitter's edge network before we expanded our network with Google and some of the issues that we were facing and how we solved them. So Twitter's global edge network is made of multiple points of presence deployed throughout the world. And we also have a global backbone network that this edge connects to. The edge then forwards traffic on to our serving regions that are located in a few different places throughout the world. When we originally deployed this network, we had different IP addresses in different locations, unicast IPs or regional IPs, and then we would have different DNS responses based on where the user was. We eventually changed this to be globally anycast FIPS, which greatly improved availability because of some of the issues with DNS caching or imprecise geolocation. So availability was good at this point. However, performance wasn't always good. So some of the challenges that we've run into are, first of all, Anycast is optimized by the carriers, by the individual service providers. They can set their own policies. Twitter can't necessarily control making sure that a certain service provider provides the best experience for Twitter users versus other users. The service provider may optimize for their own traffic or for different types of traffic versus Twitter traffic. Another issue is with capacity and with location, getting close to the users. If Twitter wants to add a new location on our network, we have to do a lot of research and we have to incur a lot of cost and engineering. So it's difficult if the World Cup is going to be in a new location where we don't have good connectivity or a good pop, a local pop. Or the Olympics are going to be somewhere, again, where it's challenging for Twitter users to connect. It's difficult for us to quickly add a new location, especially if it's going to be somewhere temporary, where we just need a burst of capacity. Let's look a little bit into some of the problems with Anycast IPs that we've seen. So with our Anycast IPs, our end users, so here, let's assume that this purple icon is a user somewhere in Europe that's trying to connect with the Twitter edge. They have the Twitter global Anycast IP, and that edge can resolve to one of n different regions, one of n different edges that exist in Europe. It's up to kind of this blob called the internet to figure out if this will go to edge A or edge B and the path it takes to get there. And this blob is actually made up of lots of different hops, individual service providers, transit providers, and various agreements between them on how traffic is routed. This can change throughout the course of a day and based on a variety of settings that are made by people frequently. So the path from the end user to Twitter is not always going to be the most optimal path. Additionally, when Twitter has to send the response back to the end user, Twitter can just choose the first hop back. Then that one may take a circuitous route back to the end user. Again, both of these directions may not be optimal at a given point in time. They could be based on time of day, network feedback, round robin algorithms, a variety of things. So this is pretty good for availability, but it's not great for latency. Furthermore, it doesn't always seem logical to our engineers, or at least to me. This chart shows where requests from users in South Korea, which Twitter edge the request ended up on in the course of a day, during the course of a day. I personally would have expected almost all of the requests to show up at our edge location, which is in Eastern Asia. We have multiple locations in Asia. I would have expected that the South Korean user requests would end up there. Turned out only about 60% of requests ended up there, where the other 40% of requests ended up going to Europe or going to the US. We also noticed a lot of deviation in the overall latency histograms, large standard deviation. Some of this is attributed to the return path that Twitter was taking, or just some of these really long paths that the user requests were taking. So improvements that we've made to mitigate some of these problems One of them has been to expand our edge by using the public cloud, specifically the Google Cloud, the Google load balancers. So this has really increased our global footprint. So however many POPs we had before, now we also have the entire Google POP network as well to ingress user traffic with all of Google's BGP optimizations and peering agreements with the various service providers and the return paths as well. Also, we've acknowledged that we can't control making sure that service providers provide the optimal path from a specific user to Twitter. So what we've decided to do is we've set up a variety of different VIPs instead of a single global Anycast VIP or a single set of global Anycast VIPs. And what we've done is we measure all of these different VIPs, and then we can optimize how an individual user connects to Twitter by finding the best VIP for that user. So looking back at this diagram again, the end user, we can give them our global Anycast VIP. They can connect through the internet through all of those hops and end up at edge A or edge B, and then we can return it to them. We can also provide another VIP. In this case, this VIP also took the same path to edge A, but perhaps in this case, Twitter's BGP policy says that the return path will always go to a specific provider. And we can measure how this red and this black path are performing over the course of the day, and we can prefer one or the other for our individual end users. We can also set up Anycast VIPs so that our user is making a request and it forces them to land on edge B in this case, or perhaps it doesn't work. We can again measure it, and we can provide this if it's a good option for the end user. Also, we can set up lots and lots of VIPs in the public cloud that route to Google edges, and then also provide Google various ways to route back to Twitter and measure all of these as well. The system we've set up that uses real-time measurements to choose from one of hundreds of different VIPs or routes back to Twitter for individual end users. We call it the traffic control tower. We steer individual users to the best VIP for them at that moment. And we use a variety of information. We use net blocks, subnets, ISP identifiers, and country codes to figure out how to group measurements together. We're able to route around problems that we see in the internet. We're able to find optimized routes from a user to Twitter and back. And it's proven very effective for us. I'm going to hand it back over to Cynthia to talk a bit about the Google network, and then we'll look at how Twitter specifically uses the Google Edge.
All right, thanks, Todd. So yeah, as Todd mentioned, the internet can definitely present itself with inconsistent behavior on the traffic path. So clearly the network matters and is really important to the end user experience. With Google's private backbone, we can provide two types of networking tiers. So there's the standard and premium tier. So the premium tier is a unique combination of providing speed and reliability, riding the Google private backbone. So the best analogy is pretty much like a hot potato, cold potato type behavior. So the default alternate behavior would be like or hot potato, getting rid of the packets and handing it off to the internet as soon as possible. Whereas with the Google Premium tier, we basically hang on to the packet as long as possible, deliver it, ride it over our private backbone, and then deliver it as close to the destination or user as possible. So this enables basically a better reliability, performance, security, and a better user experience. So one networking construct that Google provides is the global load balancer with Anycast VIP. So this load balancer can be used for global reach for users to quickly enter the Google backbone and infrastructure and traverse the private network to its destination. It provides worldwide capacity, cross-region failover, and fast auto-scaling, and the ability to provide or handle millions of queries per second. So Twitter actually leverages the Google Cloud Load Balancer for edge reachability of services. And this global load balancer can be combined with both Cloud CDN and Cloud Armor for both caching and security services while scaling. So one powerful behavior of the global load balancer is the cross-region failover, the overflow to other regions. So traffic is actually proxied to backends by a special algorithm called the waterfall by region. So if an entire region reaches capacity, the waterfall by region algorithm is triggered and traffic can overflow to the closest region with available capacity. And traffic can also be preemptively overflown to other regions in the event of unhealthy backends in a certain region. I just want to talk a little bit about NEGs, so network endpoint groups. This was introduced, actually helps a lot in containerized environments, where without NEGs, there was an IP tables rule that would hop from one node to another. So there's this extra hop introduced. Network endpoint groups is basically a collection of endpoints defined as an IP port pair. This allows things like pods to be directly reachable as backends to the global load balancer. So what's interesting about that is you can use negs in other definitions as well, like internet negs, which would align to endpoints that are actually outside of Google Cloud. So next, Todd will get into the details of how Twitter uses Google Cloud load balancing in their deployments.
Thanks, Cynthia. So there's two primary ways that Twitter uses the Google Edge. So we use Google's POP network, which is all over the world, and we accept two types of requests through the load balancer. One is layer 4 only, and the other is layer 7. So in this first example, we're looking at how Twitter uses Google's TCP proxy. So in this case, the Google Edge closest to the user that will steer the user to based on our traffic control tower system. Will terminate TCP for the end user, establish a persistent connection with a Twitter service, which is running in GCP in the Google Compute region. And then we will then proxy that TCP connection back to one of many Twitter VIPs. In this diagram here, you see there's a blue, a purple, and an orange VIP that the Twitter service in GCP will hand off to. These represent different paths back to Twitter. So some of them ride on the Google backbone as far as possible. Some of them hand off as quickly as possible from Google to the Twitter backbone or private interconnect. So in this case, using layer 4 only provides some additional security for Twitter in cases where we want the certificate to always remain in the Twitter POP or in the Twitter infrastructure. Or else it provides us with some additional compatibility if we have some Twitter clients that have special Twitter only level 7 behavior, various protocol idiosyncrasies, etc. Additionally, we use Google pretty heavily as a layer 7 proxy, and we get multiple benefits in this case. So again, we set up multiple VIPs that all correspond to the worldwide Google Edge, and the different VIPs use the internet neg that Cynthia was talking about before to route back to one of n different Twitter backend IPs. And these IPs, again, they correspond to different routes back to Twitter, either over the Google backbone or over the Twitter backbone. And again, we measure those and send the user to whichever one could be performing the best, or perhaps where we need additional capacity. And I'll talk about that shortly. In this case, as you can see, the Google Edge does everything. There's no service that Twitter has to run inside GCP. There's no deployments we have to do. There's no monitoring we have to do besides overall Google load balancer monitoring. So this has been really great for us and reduced the amount of operations and deployments that we've had to do to GCP. Let's take a look at what this has done for our end users. With a combination of the control tower and expanding our edge to regions and to locations in the public cloud, we've been able to pretty dramatically improve the performance for many of our users. This graph here shows the improvements at various percentiles, P25, P75, P99, for users in different countries. And this represents the user measured home timeline request latency end to end. So it includes all the backend latency, the connection establishment latency, transit latency, et cetera, et cetera. And as you can see, in all of these countries, we've pretty dramatically improved some of the latency and even some of the earlier percentile latencies as well. We've seen this correspond to greater satisfaction and usage of Twitter in these regions as well, as failures have gone down, and request success rate has gone up and latency has gone down. One additional benefit from using the public cloud edges, from using Google Load Balancer, has been additional capacity that we've gotten to use with no deployments on our end. This chart comes from a recent event in South America. There's a reality TV show called Big Brother Brazil that recently set the Guinness Book of World Records most online votes. It took this away from American Idol, I believe. And this purple line here shows the number of requests that happened at the peak of voting during the show, the number of requests to Twitter. And the red line on the bottom shows how much Twitter on-prem capacity we have in South America. And this peak was actually 3 times the amount of on-prem capacity that we have. So if we weren't able to burst into the public cloud and spill over into our other regions, Twitter likely would have been just hard down for the entire continent of South America. And by using the control tower to steer users to public cloud endpoints and spillover VIPs and other things that are performing well, we not only kept Twitter successfully up, but we were able to keep Twitter up with really fantastic performance for our end users at this time. Let me hand it off to Cynthia to talk a bit about the traffic director and hybrid networking.
So yeah, let's talk a little bit about Traffic Director. For those who don't know, Traffic Director is a managed control plane enabling global services with various types of backends and GCPs. So that could include GCE instances or GKE, and it programmatically configures Envoy proxies. So it actually leverages the Google Cloud Load Balancer, and thus is a powerful way to serve applications globally via the Google network. Traffic Director additionally allows for hybrid connectivity, as it has the capability to route traffic to non-GCP backends. So it's an additional way Twitter can direct traffic to its data centers. All right, thanks for watching our talk. We made it to the end. We hope you learned a little bit about how Twitter scales with Google Edge networking. Wanted to also, if you wanted more information about Traffic Director, we have follow-up talks that will dive deeper into the Traffic Director capabilities amongst many of the other networking talks. I want to also have a special thanks to Todd and the Twitter team for walking us through how Twitter Edge deployment is using Google Cloud.
Great. Thanks so much, Cynthia. And a big thank you to Cynthia and to the Google team on this great partnership. We have more resources about the traffic control tower and how Twitter uses the Google Edge in the public cloud up on the Twitter engineering blog. So check that out and enjoy the other talks. And thank you very much. This was fun. Bye.